Welcome again, beaters, to a new lesson. Well, it's not really a new lesson because it's the same lesson as the previous one, but it was getting too long, so I decided to cut the video. And here is the second part. Now we are going to see what really means this matrix, okay? Because here we defined R by the row index being an upper index and the column index being a lower index. So we are going to try to understand what's this matrix. And okay, so let's do some matrix algebra. We see that the R matrix satisfies a property, which is that its transpose is its inverse. So if we multiply R transposed times R, this is basically, I'm going to copy this really fast. And we have in the left hand side, if we have in the left hand side the transpose. Okay, now. So you can check that if you perform this matrix multiplication, you obtain the identity matrix. So the transpose is the inverse of R. Now we are going to express this into index notation, and let's do a little some matrix algebra. Let's say that we have a matrix C with two indices I and K, which is a multiplication of the transpose of a matrix A, which has indices ij, with another matrix B, jk. You can check by yourself that when you multiply two matrices, you sum over these two indices, which are the closest together. So we can do a little trick that because this is the transpose of the matrix A, the transpose by definition it's like changing the rows by the columns. So this is just A ji, we interchange the indices with B jk. So we have written this just to see that when we multiply two matrices and one is transposed, like the dummy indices, they are these two. So it's the first of the first matrix and the first of the second matrix. So we are going to do the same. In index notation, we have these two matrices, which are the rotation matrices, and we are going to contract these two indices with a Krocker delta. And this is going to give, by definition, the identity matrix. Note that we have written j and n because I, m, they are dummy indices, so the only free indices, they are j and n. So now we may multiply both sides, for example, by delta nk, and we arrive at a result which is very important, and it's that, for example, let's contract these two. We are going to kill the n's, and we are going to place the lower I here. Now we are going to do the same but for the n. We are going to kill the n, and we are going to place the k here. And now we have this, which is still the same. And here for the Krocker deltas, we are going to kill the n, and we are going to place the k. Now the Krocker delta, it doesn't matter if we write it as in these two forms, they are the same, because by definition the Krocker delta is going to be 1 if both indices are the same, and 0 if they are different. So it doesn't matter the order of the indices. So we have arrived at this important formula, which is basically that the rotation matrix times its transpose is the unit matrix. Now we are going to use it to prove what we started doing in this video, which is that the length of a vector is independent of the system of reference. So we are going to do the same. Remember that we started like writing square roots, but they don't really matter. So we are just going to work with the squares of the length. So starting in Bob's frame, we have the vector b. We are going to do its scalar product, and we are going to contract it with ij. So this is just this thing. Okay, we have a video. It was lesson 1.1.2, I think, the part 2, where we talk about the scalar product. So we take the scalar product of these two vectors, and by definition of the Kronecker delta, this is just lowering the j index and turning it into the I index. So we are going to use these formulas. We're going to put them here, and when we are going to see that this is indeed invariant. So for the first element, we really have this thing, and for the second one, we have I. Be careful, okay, because these are dummy indices, and I've already used for a dummy index the letter J. So if I write here the letter J, it's going to be all a mess, because I don't know if this letter J is related to this one or to this one. So when you have already written a dummy index with a letter, don't repeat that letter. Now we can change the order of the factors, and we have this thing. So now you can identify this with this equation. So this is really delta kj vj vk, which is simply vk vk, and this is just, well, the contraction, the scalar product of the two vectors. So we see that this is an invariant when we transform upon rotations. Now, very important, we have been using for raising and lowering indices the Kronecker delta. So the Kronecker delta is a good tool for raising and lowering indices, but because we are in flat space, we are going to see in, I don't know what lesson is, maybe 1.1.6, I think. We are going to see that the object that we use for raising and lowering indices is not the Kronecker delta, it's the metric. Okay, so the metric is the object that defines space and how it's like curved. So we have been working in flat space, which isn't curved, and it happens to be that the metric in flat space is the Kronecker delta, and that's the reason we have been using this for raising and lowering indices. You might have compute in paper in your home that the components of these two objects are the same. So you might think, wait, you told me at the beginning of the video that covariant and contravariant objects, they transform differently, but I have computed the components of these two objects and they are the same. So they transform equally. And also, if you compute, if you have a vector vi and you calculate the components in the covariant form, you are going to find that they are also the same. And this is like the main reason we have been in the past lessons only using lower indices, because if we have the Kronecker delta as a matrix, it's exactly the same having upper indices than lower indices. But it's important to take into mind that it's the metric, the object that we use for raising and lowering indices. It's only been in this lesson that we have used the Kronecker delta. So I'm going to do as a little cliffhanger for the next video. We haven't talked about bases for vectors. So Alice has a basis E1 and E2, and Bob has his own basis E1 prime and E2 prime. And a vector by itself is a geometrical object. So we may express a vector in this form, which is Alice frames of reference, or in Bob's frame, and it's still the same vector. So it's not only that the length of the vector is invariant, it's that the vector itself is like a geometrical object, and all those kind of things of vector bases and components that we write to express the vector, it doesn't have anything to do with the vector. The vector is something like by itself, is a geometrical object, and we use components and bases to express that vector. As a fact, you can see that when we do a rotation, I'm going to another page. So let's say that we have a rotation which is 90 degrees. Okay, so the rotation matrix is going to be 0, 0, minus 1, 1. So Bob's reference frame is going to be this and this. Let's say that we have our vector b to be 1, 0, and we are going to transform it. Okay, so we are going to do a little example, because I mean all of this is very beautiful and everything, but an example is always good to see how everything works. So our vector in Alice base, of course, is going to be 1, 0. Now we already know, because this is a very simple example, that in Bob's base this is going to be just 0 minus 1, because we're going to put ourselves into Bob's perspective. So Bob sees this, because Bob has his own I prime axis and x prime axis aligned in this way. So he sees that the vector b is pointing downwards. So we are going to check that this in fact works. So b prime is going to be r times b. This is in matrix notation, and this is basically 0 minus 1, 1, 0, and we have 1 times 0, which is 0, plus 1 times 0, which is 0, minus 1 times 1, plus 0 times 0, this is 0, and we have in fact that b prime is 0 minus 1. Okay, I've made this example because sometimes we find the minus in the rotation matrix written in the upper right corner instead of the down left. This is because what we are rotating isn't the vector, we are rotating the axis. And you can see that when we rotate the axis in this way, the vector, it rotates into the other way. And now you might think that, well, the axis, it has attached the unit vectors, and what we see rotate in the other side are the components. Thus, it makes sense that when we perform a rotation, the axis goes into like this way, and the components go into this other one, therefore it's invariant. So like the geometrical object, by definition of the components and the basis, they are invariant. This is why the basis is covariant. But we'll see this in the next video, okay? So see you in the next lesson. Bye.